In our last video together, what we discussed was this concept of aromatic and anti-aromatic and non-aromatic. Okay, so we talked about the differences between these definitions, and we also discussed a little bit about, well, what if carbon has a positive charge, or what if carbon has a negative charge in the ring system that it's in? How do we handle those? So in this video, what we're going to focus on is section 820. And section 820 is going to refer to heterocyclics. All right, now let's talk about heterocyclics, because this is going to be kind of a different type of environment than what we've been using in the past. So cyclics basically means a ring system. So I'm just going to draw a 6-membered ring system, and this is normally what we would do. And we would assume up to this point that all of these atoms in the ring are carbons. However, heterocyclics, what does hetero mean, folks? Hetero means different. So a heterocyclic ring is a ring with different atoms. Comes from the Greek word heteros. All right, well, this ring system, that means that one of these carbons, or maybe more than one, is going to be substituted for a different type of atom. So it's not carbon all the way around anymore. So that means that one of these carbons could be a nitrogen, or could be a different atom that we commonly would find in a ring system. So with the heterocyclic rings, there's 3 atoms that are going to show up the most. And this is nitrogen and oxygen and sulfur. These 3 atoms really take place in the ring, and they're very common. And it's not surprising that we will see these throughout our time together. So carbon, of course, is the basic foundation of the ring system. But we can substitute one of these carbons for an N, an O, or an S. All right, so we need to know how to handle these, right? I mean, if we're talking about aromatics and anti-aromatics and non-aromatics, then we have to get comfortable with the idea that one of these could be something other than carbon. So how do we handle this? Well, I'm going to show you a trick that I like to use for myself. All right, so they might give you this type of structure, and they'll say, label this compound as an aromatic or a non-aromatic or anti-aromatic. Okay, well, number 1, is it a ring? Yeah, it's a ring. Ding, ding, that works. Okay, number 2, is there an odd number of double bonds? So we see this and we say, yeah, double bonds or pi set of electrons. So we look at this and say, yeah, there's 3. I mean, I can count those, right? There's one here and there's one there and there's one there. So there's 3. So that's an odd number. And then the next one is every atom of the ring an sp2 orbital? Okay, well, that means this carbon's a double bond, and this carbon's got 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 a double bond. But what about this nitrogen? It's not a carbon, is it? So do these have different rules that they bring to the game? Because they are a different atom. So do we look at that nitrogen and say, yes, you meet the criteria because you're sp2 hybridized? This is how I need you to think of this. This is the trick that I'm going to tell you to use from this point on. Where the confusion happens is the set of electrons. Okay, so here's the key. If that heterogeneous atom, the N, the O, the S, or something else that might be in there, if it has an electron pair, if it can donate, if it needs to donate the electron pair, it can. And if this happens, then we say, yes, we need to count that electron set. And this is also a sign that this is sp2 hybridized. If the atom has an electron pair and it doesn't need to donate that electron pair, then no, we don't really count that as an extra set or an extra double bond. So let me kind of show you a trick. And this is going to go through and maybe make this a little bit better. If I look at this structure the way that it's written, the question is, do I need to donate this set of electrons to the system in order for this to be delocalized? And the answer is no. It's delocalized the way that it already is. There's nothing that I need to do to it. So because of that, this meets the definition of aromaticity. It is a ring. Everything is sp2 hybridized because I see a orbit there that has a free set of electrons in it. And that free set of electrons, well, that's kind of hanging out, kind of on its own. We don't need to donate those electrons to the ring because that nitrogen already has a double bond that's associated with it. So we look at that and we say, okay, it's sp2 hybridized. And there's an odd number of double bonds. And if you did this molecule, it would be flat. So it meets all the definitions of an aromatic ring. So this is the question. Always, do I count these electrons or do I not? Okay, so let's do another example. Let's take a look at this ring system with a nitrogen here, and we have a hydrogen and a free set of electrons there, and we do a line here and a line there. Is this aromatic? Well, we just learned our words, so this is a heterogeneous ring. Okay, so this is a heterogeneous ring, which means there's a nitrogen there. Is it a ring? Ding, ding. Yes, it is. Number 2, is everything sp2 hybridized? All right, well, that one is, and this one is, and that one is, and this one is, and this one is a big O question mark. Right now, it doesn't look like there's a double bond associated with it. So is it an sp2 hybrid or not? And in addition to that, right now it doesn't really follow Huckel's rule. There's an even number of double bonds that are associated here. Okay, so does that nitrogen meet the definition of an aromatic? This is how you determine the answer. Does it have a free set of electrons that it can donate to participate in the delocalization of the system? And the answer is yes, it does. Here is a double, single, double cause you trouble, and then it goes back to single. But folks, there is a free set of double bonds that are there, which means that those sets of double bonds can participate in the hydrogen bonding, or not the hydrogen bonding, but in the delocalization. And those electrons can help move all around the molecule. So this does satisfy the need for the third, which would be the odd number of double bonds or pi electrons. So the answer here is yes, this is an aromatic. And even though this nitrogen does not have a double bond that's associated with it, it's perfectly okay because that set of electrons can participate. So the trick here is, if it has electrons, does it need to use them? If it doesn't need to use them, then it's not going to use them and everything is perfectly okay. Well, let's take something else that we kind of worked with so far, and this is a cyclopentane ring, but here's an oxygen instead of a nitrogen. All right, so this oxygen's got 2 sets of electrons here and a double bond there and a double bond there. So let's say that this is the molecule, and we need to figure out, is this aromatic or not? Number 1, is it a ring? Number 2, is there some double bonds in it? Okay, well, is there an odd number? We've got 1 and we've got 2, but that's about it, right? So we see this oxygen, and I treat oxygen the same as nitrogen. Does that oxygen have a free set that can participate in delocalization or not? And the answer is yes, it does. There is a free set there, and that free set can help participate in the delocalization, so we get complete delocalization around that entire molecule. So we do count that as our addition. So that will be 3 double bonds, which is my odd number. And because they are participating in that delocalization, then they are going to be in this p orbit as well. So here, ding ding, yes, that is an aromatic molecule. All right, well, I told you NO or S, right? So let's put sulfur here. Well, folks, the description doesn't really change any at all. So if I just remove oxygen and put sulfur there in its place, we treat sulfur the same way as we do nitrogen and as we do oxygen. There's no difference there. So here's a ring system. This is a ring. Ding, ding. There's the first one. Number 2, is there an odd number of double bonds? That's Huckel's rule. So if I look at this, we've got 1, 2, and where's my third one? So I see the electron pairs at sulfur. And can sulfur donate one of those electron pairs? And the answer is yes, it can. And this will help improve the delocalization throughout the entire molecule. So we get double, single, double, single, double, single all the way around that ring. Because of that, everything is sp2 hybridized. Those electrons are in the p orbit, and they begin to share all the way around that ring. So it meets the definition yet again of an aromatic. So guess what I'm going to do? I'm going to do ding ding. That works. All right. So there is another heterogeneous ring that has sulfur, and we counted the electrons when we need to count the electrons. Now let's take a look at these molecules that we have here. The two to the right-hand side, these are purine and pyrimidine. And purine and pyrimidine, folks, this is kind of the base of DNA. So as you start to assemble DNA in your body, your DNA strands are composed of various bases that we call A, T, G, and C. And these are the foundational building blocks that those adenine, thymine, guanine, cytosine kind of build upon in the DNA strand. So purine and pyrimidine, very common bases, but they're heterogeneous, right? They are ring systems, and those rings have things other than carbon in them, and we can see that. The problem here is that they're going to try to make it more complicated for me. So over here to the right-hand side, we're going to wait off in just a minute, and we're going to focus on these two molecules last, because they do look more complicated than some of these others over here on the left-hand side. All right, so let's take a look at this one over to the left, quinoline. All right, so this molecule, is it an aromatic? Okay, the answer is yes. So up here at the top, look at the title of the slide, aromatics. Okay, so that means that all of these are aromatics. Let's kind of go through and figure out why they are classified as aromatic. Okay, so first, this is a ring system. I can visually see that. That's no question at all, right? If you cannot see that this is a ring system, then you just need to go ahead and say, bye-bye, I'm out of here. I'm not learning squat. All right, so here we see the structure. It is a ring, and this ring structure, I've got an sp2 and 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 an sp2. All right, so all of those carbons have a double bond associated with them. They're all sp2s. Now, what about this nitrogen? Well, if I look at this nitrogen, I see the double bond on it. So this nitrogen probably is going to be SN2 because the double bond is there. Now, the next thing is, what about double bonds? Do we have an odd number? All right, well, I've got 1 and 2 and 3 and a 4 and a 5. Do I count these free pairs? No, because they're not needed. Only if they're needed for the delocalization do I need to count really the free pairs. So the way that this is structured, it is double, single, double, single, double, single, double, single, no matter how you go around these rings. So that is why this is an aromatic compound. So that's how we handle these weird atoms that are not carbons in the ring systems. Indole. All right. So let's take a look at this structure. I'll do the same thing. Is it a ring? Yeah. Okay, next. Are there sp2s? All right, well, here's 1, sp2, 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 sp2. There we go. Now the question is the nitrogen. Do we count that as sp2 or not? Well, it does have a free set of electrons, and we'll count those free sets of electrons only if they are needed. All right, well, in this case, this nitrogen does need to use them because these electrons if they are allowed to participate in the ring and go and play with all the other little electrons, then this does complete the delocalization in that ring, because the rules of delocalization said a double bond can move toward a free set of electrons. That was Chem 251 stuff in Orgo 1 first semester. Right there you go. So because we do need those electron pairs, we count that electron pair as a sp2 pair. So what that means, I've got 1 double bond, 2 double bond, 3 double bond, 4 double bond, and that set counts. And this is our 5th double bond, so that is a sp2, and that has a double bond, quote unquote, associated with it, and that will be playing in the p orbit. So indol is an aromatic compound. Let's look at the next one, imidazole. Very common base, typically an organic, nitrogen-containing species. We have a whole lecture topic on nitrogen-containing compounds, by the way, so these are just a few. So is this an aromatic? The answer is yes, it is an aromatic. All of these are aromatics, but let's kind of figure out why. Why is it classified as an aromatic? All right, so ring. All right, next is everything double bonded. So I see an sp2 and an sp2 and an sp2 right there. So all the carbons are. The questions are the nitrogen. So how do I handle the nitrogens? Well, this nitrogen has a double bond on it. So yes, that one's going to count as sp2. That one's kind of very clear cut. There's an sp2. I see the double bond. Next over here on this side, is that nitrogen classified as an sp2? Well, one of the key indicators here, does it need to provide a set of electrons to complete the delocalization, yes or no? If it does, then that will be our 3rd double bond, and that means that that nitrogen will be sp2. So the answer, yes. Here we have a double, and then a single over on the left, and then a double down below on the left, and then a single to the right at the bottom. And then we get to this nitrogen, and that nitrogen doesn't have a double bond. It cannot complete the double, single, double, cause you trouble. But it could if we provide you those electrons to the ring. And there is our double, single, double, single, double, single, double, all the way around the ring. So because of that, it meets all the definitions or the criteria of the aromatic, and this is an aromatic compound because of that. All right, so this one, we didn't have to worry about the electron pairs because it didn't need it. It had a double bond on it. And then over here to the right-hand side, we do count those. And the reason we count them is because it needs to donate them to complete delocalization. And that's the very good sign and trick that we use to determine if it is an aromatic or not. All right, next are the purines and pyrimidines. Let's do pyrimidine first. So this pyrimidine is a ring structure. You can clearly see that. And as I go around, sp2, 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 all the carbons are sp2s. Those were not a question. The nitrogens, that nitrogen has a double bond, sp2. And then this nitrogen at the bottom, it has a double bond, sp2. So really, everything is sp2. And then if I take a look at the double bonds that are in the ring, there's 1 and 2 and 3. So there's an odd number. It meets Huckel's rule. So ding ding, that is an aromatic, just like what we expected, because that's what the title up here told us that it was going to be. Now let's take a look at purine and kind of go through that decision-making process too. Is it a ring? All right, next. Is all the carbons sp2? All right, well, that one's an sp2. This one's an sp2. That's an sp2. This is an sp2. That's an sp2. They all are sp2s. All right, well, what about the nitrogens? Because those are the weird ones. Do we count those or do we not count those? Well, that nitrogen has a double bond. So, yep, that's an sp2. This nitrogen has a double bond. So, yep, that's an SN2 as well. And this nitrogen up at the top, it has a double bond. There's my extra sp2. And then this nitrogen here, there's no double bond right there. right? But it does have a free set of electrons. Do I count those electrons? And the answer is yes. And the reason I count them is because if I include them in the ring, that completes delocalization, doesn't it? I get a double, single, then a double, then a single, then a double. So I do complete delocalization if I provide those electrons to the ring, which means that this nitrogen is going to end up being sp2 because it has a set of electrons in a p orbit that it can donate to the delocalized network. That's how this works. So it is a ring system. Everything is sp2, and now I count the double bonds. I hope I get an odd number. So here's a 1 and a 2 and a 3, and then this one is a 4, and that set of electrons will count as my 5th. So that is an odd number, which means it meets Huckel's rule. So every one of these folks is an aromatic molecule, and that is how we go through and determine whether or not these heterogeneous atoms are contributing to the aromaticity or not. Oxygen works the same way. If I go through and put oxygen in each one of these, folks, our decision process stays the same. You look at the oxygen, you see 2 sets of electrons. Can those electrons be donated to the ring to complete delocalization? If the answer is yes, then you count them as a double bond and you assume that these are going to be sp2. And sulfurs are the same exact way. All right? So don't let these heterogeneous rings fool you. They are no more complicated than all of the other examples that we've done so far. They just have things other than carbon. And because of that, people freak out and they just kind of go crazy on me for a little bit until they get used to the idea that it doesn't have to be carbon there. It is okay. There are tons of compounds. Those compounds do not have to listen to you. Those compounds do not have to take orders from you. They're going to be made the way that they want to be made, and you're either going to like it or you're just going to have to just truck on and ignore it because that's just the way that it is, folks. And that's how life is too sometimes, right? Okay, so finally, we are getting to a point that we can get into our real lecture of aromatics. Oh God, I know what you're thinking. What have we been doing all this time? We've just been playing catch up a little bit. We've been going back and pulling out these extra sections from these other chapters that we haven't talked about, and I just kind of lumped it all up into a nice little preemptive package for you. So now we get to focus on really the heart of the chapter, and the heart of this chapter and the lecture is benzene. Now you know a little bit about benzene. Aromaticity, you now know what an aromatic means, and now we need to learn how to name these things, right? Now that we know we have an aromatic, now that we know the rules of designating whether something is aromatic or not, we now need to go through our traditional type of lecture material. How do we name them, and how do we react with them? And now we're going to learn how to name these things. You're going to find out this is not very difficult, though. If you could make it through nomenclature in Orgo 1, you'll be perfectly fine in this nomenclature as well. No more complicated at all. Actually, I think it's easier. All right, so with that said, I'll see you in the next lecture video. Whenever you're ready, I'm ready. You hit that play button and you keep trucking on and you keep cracking those knuckles and you keep writing down those notes. You make me very, very happy. Good job, folks. Good job.